Hi there folks, today we're looking at trapezoids and kites, and these are just a couple more of our special quadrilaterals that we've been dealing with. So a trapezoid is just a quadrilateral with exactly one pair of parallel sides, and it's really important that word exactly one pair. It means I can only have one pair, no more than that. Alright, so when I look at a trapezoid, I see a set of parallel lines. The other sides cannot be parallel to one another. If those were also parallel, I'd be dealing with a parallelogram, and it would no longer be a trapezoid, okay? So, when I'm looking at this thing, notice I have that these sides are parallel to one another, and the sides that are parallel to one another we call the bases of this thing. So we have two bases when we're dealing with a trapezoid. So the two sides that are parallel, we call those the bases. The sides then that are not parallel, we call the legs. And so this is similar in terms of the terminology that we've used when we were dealing with triangles. Well, the triangle only had one base, and but I still had two legs. Now I have two bases and two legs. All right. Along with that, we'll talk about the base angles of this thing. Really, we have two sets of base angles. So like these guys would be a set of base angles because they share a base. And then separately, these guys would be a set of base angles because they also share a base. Alright, so when we start talking about the legs of this thing, those are the non-parallel sides. The bases are the parallel sides. Then we talk about the base angles. They're the angles that share a base. Alright, and so when we look at this, we've got a couple theorems here. And these first two theorems deal with isosceles trapezoids. And when you think about the word isosceles, when you think about a triangle, an isosceles triangle is when the legs are the same. And the same thing is true for a trapezoid. An isosceles trapezoid is when the legs are congruent. So if a quadrilateral is an isosceles trapezoid, then each pair of base angles is congruent. And again, we have two sets of base angles, so we're going to have two separate sets of congruent angles if we're dealing with an isosceles trapezoid. Alright, so the two angles that share a base are congruent, and that's true for the other base as well. The next one we have also deals with isosceles trapezoids. So again, these do not deal with all trapezoids, just isosceles trapezoids for these ones. If a quadrilateral is an isosceles trapezoid, then the diagonals are congruent. So when I draw those diagonals, those are congruent. And really, we're not going to go through the proof of these, but it's really easy if we talk about an isosceles trapezoid. If we know that these guys are congruent, and we know that those are parallel, we can start dropping perpendiculars here. And once we drop that perpendicular and we have these right angles here, what we end up establishing is we can easily prove that this guy in here is a rectangle, which then allows us to prove that these two triangles are the same, these little triangles on the end, and then we can easily prove that the base angles are the same. Very similar to that, when we do an isosceles trapezoid again for this one. Oh, that is that's terribly drawn. Let me try that again. That's not much better, but I don't feel like redrawing it. So if we were dealing with another isosceles trapezoid, again, if we were to establish these diagonals, it becomes very easy to prove that these triangles are congruent. And once we have the triangles congruent, we can start to talk about the diagonals being congruent. Alright, and it's really easy to do that once we establish the previous theorem and we have those base angles being congruent. It's easy to prove that those two triangles are congruent, and we can go from there. So we're not going to go through the proofs, but that's a quick explanation of where they come from. For example, if I look at something like this guy, it asks me to find the value of x, and then we're actually going to find some of the measurements of some of these angles as well. So when I look at this thing, the first thing I notice is that this is a trapezoid because I have one pair of parallel lines here, which means that I have a trapezoid. That's the definition of the trapezoid. And then it's an isosceles trapezoid because I've got these congruent legs. So now I know it's isosceles. So if it's an isosceles trapezoid, I know that these base angles, this guy and this guy, have to be congruent. So I'm just going to take those off to the side and set them equal to one another. So I've got the x squared minus 8 equals the 7x. And then from there I would just subtract the 7x from each side. And now I'm solving a quadratic, so I build a bridge. Again, when you do this, you build a bridge. That means you multiply first and last. Two numbers that multiply to a -8 but add to a -7, or a -8 and a +1. So then this is going to factor into an x minus 8 and an x plus 1. And now all I do is set each of those factors equal to 0. If I do the x minus 8 equals 0, I'd find out that x equals 8. If I did the x plus 1 equals 0, I'd find out that x equals a -1. And again, we should always be a little bit wary of negative answers here. I can have a negative x value, but I can't have a negative angle measurement. And you should notice right away that when I go to plug this thing in right here, it's going to give me a -7. Well, that doesn't work, so I can just toss that answer. So that one's no good. So the only answer I get here for x is the 8. And again, I can check that by plugging it back in. And really, we need to plug that back in for the next part of this thing. So right here, if I plug that guy in, it gives me a 56 degrees right here. If I plug it into the next one, 8 squared is 64, minus 8 is also a 56, so I get 56 degrees. What just happened there? Something went a little funny. Let me try that again. And so what I see here is that those base angles are congruent, but then it asks me to find the measure of angle B and angle C. So this guy right here and this guy right here. And hopefully it's obvious where we're going to come up with those. Keep in mind again that these are parallel lines. And if I know that these two lines are parallel, that means this leg is a transversal. So when you compare angle A and angle B, you should notice right away that those are same side interior angles, which means they are supplementary angles. So that means that this angle A and angle B have to add up to 180, which means the measure of angle B has to be a 124 degrees. And since we know that B and C are base angles of an isosceles trapezoid, those are congruent as well. So this is 124. This guy's also 124. And again, that's just because looking at this thing, I see parallel lines. I have same side interior angles. They're going to be supplementary. Okay? If I look at the next one, it tells me that BD is 3D plus 9 and CA is 7D minus 7. And I want to find the length of AC. And once again, I have a trapezoid because I have one pair of parallel sides. It's an isosceles trapezoid because the legs are congruent. And so if I have an isosceles trapezoid, it means the diagonals are the same. And that's what they've given me here. They've given me the lengths of the diagonals. So I can just set those equal to one another. So 3D plus 9 equals the 7D minus 7. And now I can solve this thing. I end up with a 4D equals a 16. I divide each side, and I find that D equals 4. But that doesn't answer the question. It asks me what the measure of AC was. So I have to plug this back in, and I can plug it into either one. I'll just plug it into this guy right here. So I have 7 times 4 minus 7, which is going to be a 28 minus 7. So that's 21. So now I know that the length of AC is 21, and that's it. Okay? The last theorem we have for trapezoids, and this one applies to all trapezoids. This isn't just isosceles trapezoids this time. So, and this one actually has a special name, trapezoid midsegment theorem. If you remember, a midsegment connects the midpoints of the two legs, and we've dealt with mid-segments in terms of triangles before. This is going to be pretty much the same thing. It connects the midpoints of the legs of the trapezoid this time. So if a quadrilateral is a trapezoid, then the mid-segment is parallel to the bases, so that's one of the things that it establishes, and the length of the mid-segment is half the sum of the lengths of the bases. And so we get two things here. So when I draw the mid-segment, when I connect those midpoints of the legs, that mid-segment is going to be parallel to the bases, so I'm going to have a third parallel line here. But also, if we want to find the length of that thing, it's half the sum of the bases. All right, it's almost like the average of the bases. We add them together and divide by 2. So here it is in kind of a diagram form. So we can see that I'm connecting the midpoints here because these pieces are congruent. Same thing on the other side. I've got the midpoint there, so I'm connecting the midpoints. That line that's in the middle there, the one in green, that's my mid-segment. It's parallel to the two bases, which I've called B sub 1 and B sub 2. And then establishing the length of that thing is this guy right here. And that's what the second piece of that theorem is saying. It's saying, hey, if I add those together and then divide by 2 or add them together and multiply by 1/2, that gives me the length of the midsegment. Okay? For example, here it asks me to find the value of x and then find the measure of angle 1. So we're going to use the fact that we have parallel lines here to find the angle measurement. We're going to use that 1/2 b sub 1 plus b sub 2 to find the value of x this time. So when I look at this guy, first of all, let's find x. So the midsegment is just going to be 1/2 the sum of the bases. So it's going to be 1/2, or x is going to equal 1/2 b sub 1 plus b sub 2, which is the 15 plus the, what in the world is going on there? My marker's changing color mid-sentence, or mid mark there. So I just add those together. So it's like I'm adding together and dividing by 2. It's the average of these things. And now I just have to simplify this guy a little bit. That gives me a 22. 22 times 1/2 is an 11. And that's it. So that's the value of x. And then in terms of finding angle 1 here, the thing that I have to understand is the midsegment is parallel to the bases, so this line is also parallel. So when I look at the 115 degrees and angle 1, I just have to establish what kind of angles those are, and those are corresponding angles, and I know that corresponding angles of parallel lines are congruent. So the measure of angle 1 is also going to be 115 degrees because those are corresponding angles. If I look at the next one, I'm going to do the same kind of thing, except this time I'm given the midsegment as 20. I want to find the other guy. Well, how can I know for sure that this is a trapezoid? Well, I could kind of think of this in terms of parallel lines, and really it's easy to establish that this thing has to be a trapezoid and that this guy has to be parallel to this thing. So I now know that this thing is the midsegment. I know that that other line is parallel. So I go from here and I just say, okay, well, the midsegment, which is 20, equals 1/2 the sum of the bases, which this time is 28 plus x. And now I just have to work backwards and solve for x. So the first thing I would do is probably multiply each side by 2 to get rid of that fraction. So over here I end up with a 40. Over here I can do this in any order I want. The 1/2 and the 2 are going to cancel. And then from here I just have to subtract the 28. And when I subtract that 28, I end up with x equals 12. So now I've got that guy. I've got 12 here for x. And then from there, I want to establish the measurement of that angle. Well, since I know all these lines are parallel, these guys would be corresponding, so this would also be a 135 degree. And then from there, once again, my marker is it's going crazy on me. From there, when I look at this thing, because those lines are parallel, those are same-side interior angles, they have to be supplementary, which means then the measure of angle 1, if one of those angles is 135, the other one has to be a 45 in order to give me 180. So again, these are same-side interior angles. Those guys have to be supplementary. Okay. Circle some of my answers, or put a box around some of my answers here. There we go. And then looking at something like this guy, same kind of thing. I want to find the value of x. This time I didn't ask about any angles. We're just finding the value of x. But we set it up the same way. The midsegment, which in this case is x plus 2, equals 1/2 the sum of the bases. And this time the bases are a 4x minus 10 plus an 8. And now I'm just going to simplify. That's going to be an x plus 2 equals. This guy over here, I'm going to simplify what's inside the parentheses first. That's a 4x minus 2. And then from here, there's a couple different ways you can do this. I'm going to go ahead and distribute the 1/2. So I distribute the 1/2. That gives me a 2x minus 1. And now I can finish solving this thing. I would subtract the x from each side, which gives me x. I would then add the 1 to the other side, which gives me a 3. So I find out that x equals 3, and that's it. And I can easily plug that back in and check it to make sure that that midsegment is 1/2 the bases added together. So that's our special properties for trapezoids. Next, we're going to look at kites. And a kite really looks like a kite when it's all said and done. Well, imagine that. We call it a kite and it looks like a kite. That's amazing. But anyway, the kite is defined this way. It's a quadrilateral with two pairs of consecutive sides that are congruent, but no opposite sides that are congruent. Okay, so if the consecutive sides were congruent and opposite sides were congruent, I wouldn't have a kite anymore. I'd have a rhombus. All right, I'd be back to a rhombus at that point. So we have to put that restriction in there of saying no opposite sides can be congruent. So the consecutive sides are congruent, but opposite sides are not congruent. And so this is what a kite looks like. And notice here I've got consecutive sides, two sides that are one right next to each other that are congruent. Here's another pair of consecutive sides that are congruent. But notice the opposite sides, these guys that are opposite one another, are not the same. All right, and that's what establishes that this thing is a kite. All right, kites have a couple of special properties here. The only one we're really going to look at today is this one right here. It says if a quadrilateral is a kite, then the diagonals are perpendicular. And really that's the only one we need. We can establish a lot of other things from there. But once we know that, it's pretty easy to establish some other things and prove some other things. And the way this works, really, again, we're not going to do the proof here today. I'm going to get away from these a little bit. But if I have these diagonals running through here, it's pretty easy to establish that these are perpendicular to one another when you look at these guys being congruent. Because again, you could think of this as isosceles triangles, and we know that an isosceles triangle, if you bisect that thing, if you go perpendicular to the base, it bisects it. So one of these is going to be bisected, but really the easiest way to establish this is you know that when you have two congruent pieces, they're always going to be the same distance from the perpendicular, and so it becomes easy to establish that this line right here is perpendicular because these guys right here measure the distance to that thing. And so when you think about it, if you have two congruent pieces, if you were looking at these as the congruent pieces, they have to be the same distance from the perpendicular, and really these are measuring the distance. So there's a couple ways we could establish that. We could easily start looking at this thing in terms of establishing congruent triangles and things like that, but really it's not too bad of a proof if we wanted to go through it, and there's lots of different ways that we could come up with that proof. And this is similar to the property we had with the rhombus. Obviously it's not a rhombus, but it could be similar. We could prove it the same way we did the rhombus using those two isosceles triangles. So with this one it says find the measure of each angle, and this is the last example we're going to do. So we want to find the measure of each angle. Let's start with the measure of angle 1. So the measure of angle 1, that should be the obvious one. Since I have a kite and I have the diagonals drawn, the diagonals are perpendicular, which means these intersect at a right angle, which means angle 1 has to be 90 degrees. So angle 1 is 90 degrees. And that comes right directly from the theorem that we have. And then from here we can find angle 2 pretty easily because we have a triangle here, and we know that the three angles inside a triangle have to add up to 180. So if we know that angle 1 is 90 degrees, we know that the angle that's labeled as 52 degrees, we know that the last angle, angle 2, has to be 38 degrees. And then from here, angle 3 is a little bit trickier, but again, if I were to redraw this thing, if I were to just redraw a piece of this thing, just this piece right here. Okay, so I'm redrawing that piece of the kite. So this was angle 2, this is angle 1's out here in the middle somewhere. But we know that these two pieces are congruent, which means this is an isosceles triangle. So now what we automatically know is this guy right here, this angle, is the same as angle 2, so that one's 38 degrees. And then from there, if we know that that's 38 degrees, if I bring that back up here, so let's say this guy right here is 38 degrees, Well, we know that this is a right angle, so I have two triangles that are obviously congruent in terms of the angle measurements and things like that. So from here I can establish that angle 3 is also a 52-degree angle, because once again, if I look at that triangle individually or if I compare it to the other triangle and realize it's congruent, either way the angles have to add up to 180, so I could establish that that's 52. But hopefully I recognize that those two triangles are congruent based on some of the information that I have. We could do angle side angle, or angle side here is I guess the one that we have pretty readily available. Okay, so hopefully you start to see some of the other properties that we could easily come up with. Yeah, we know that those diagonals are perpendicular, but hopefully we can see how easy it is to establish congruent triangles and what that tells us about some of the angle measurements that we're going to find in here. Okay?